Hi everyone, today we're going to talk about variable types and data presentations. There's many different types of variables in research, and sometimes you'll see these variables kind of organized in different manners. For this class, this is how we're going to categorize it because this is the most common. There's two main types of variables. There's continuous and there's categorical. Continuous variables are variables that are along a continuum, kind of like a ruler where you can measure the width or the height of something. Continuous variables are like weight or blood cell count. If you think about a ruler, there's really an infinite number of possible values along that continuum. Whereas with categorical, there's really only a certain number of categories. And so with categorical, there's three different types under that variable type. There's nominal variables. Nom is like name. And so nominal variables are where we're naming different variables, but there's really no order to it. Kind of like red, blue, yellow, or if we're looking at racial categories or cities or states, there's no hierarchy to it. With ordinal variables, this is where we are kind of defining variables, like low, medium, high. And then there's dichotomous. Di is like shaking a dice, where there's two dice, or we also call it binary. These variables only have two possible answers. So it might be yes, no, positive, negative, pregnant, not pregnant, diseased, not diseased. So it's really there's only two possible answers. Ordinal and continuous variables frequently get confused as to how do we define, is it an ordinal or a category or a continuous, with ordinal and continuous variables, they do look very similar, but in ordinal, we really don't know, is the difference between, like situation A, is the difference between bad and neutral the same as the difference between neutral and good? And so if our three categories within an ordinal variable is good, neutral, and bad, we can see that situation A, there's a smaller difference between bad and neutral than there is between neutral and good. Whereas in situation A, if we're looking at how people are feeling, let's say, and we say on a scale of 1 to 3, how are you feeling? For this scale, we can see that there's a consistent difference between the continuous variables, whereas with the ordinal variables, we really don't know, is the difference between the categories in the order consistent. So ordinal variables, we say that the intervals between the variables are unknown. One thing that sometimes happens is we can have a variable, but that variable can be listed or measured in many different ways. Or the researcher may collect the data one way and change the type of variable to another way. For example, if we're looking at body mass index, if we measure the body mass index and it's 27, this would be a continuous variable. Whereas if we decide that we want to put it in a category, 27 would fit in this category, which indicates overweight. Now, if you look at these categories, they're in order, so that would be considered an ordinal variable. We also could dichotomize the variable and say that the BMI is abnormal versus what would be an ideal or a normal BMI. And so see how the same information can be represented in different types of variables, can be represented in different ways. Categorical data can be presented in many different ways. These are just some of the different ways. We can look at tables here. This is just yes, no, so it's binary data. Here's the absolute frequency, meaning the total number. We look at the relative frequency, which is the percent. Categorical data can look like this in a bar graph. So here's our yes, here's our no. We can also look at pie charts. Blue is yes, green is no. So there's many different ways that categorical data can be presented. One thing that is sometimes confusing, and I see this named wrong in research articles sometimes, excuse me, is the difference between a bar graph and a histogram. A bar graph, you'll notice, has space between the different bars, whereas a histogram does not. The reason for that is with a histogram, this is typically in ordinal fashion. And so we see that there's an order to these bars. This is, first category is people who are 60 to 65, 65 to 70, 70 to 75. And so the order is, we can put them all together because they are on a continuum, let's say. Whereas when we look at the bar graph, these definitely have very specific categories, different languages that people would speak. There's no reason why they would touch each other, or they're not on a continuum. When we look at continuous data, notice that this is data trends over time. So we're looking at a number of students and in different months of the year. This is data trends over time. One thing I want to point out is these aren't bar graphs, and we see a line connecting them. The reason for that is it's assumed that there is a continuum, and that, let's say, between March and April, we see somewhat of a straight line, that between there, if there were data points, if we saw dots on this, that it would fall somewhere on that line. And so there's an assumption that from one data point to the next, that the line would represent where we assume the data would fall. Excuse me. We can compare continuous variables. So this is comparing age versus average donation. So now we're looking at two different variables and kind of mapping out what those two different variables look like, one compared to the other. And what we see is that at a higher age, we have a higher donation. We also can look at data range within a sample. This is a box and whisker plot. I'll talk about that in a minute. With this, we're looking at one variable, diastolic blood pressure. Here's the median. Sometimes it's a mean. Here's the range of interquartile range with a minimum and maximum. Here's comparing different continuous variables. So this is looking at height versus weight, and now we see several data points in the middle there. When we look at all of these, we're really looking at univariate analyses here and bivariate analyses here. So with this, we're measuring number of students. Granted, it's over time, but it's one variable that we're interested in. So over time, we're just measuring along, which is why it's called univariate. When we're comparing variables, two different variables, one to the other, now it's called bivariate because there's two variables that we're measuring. Here's univariate again. This is only talking about diastolic blood pressure. Here's bivariate, weight versus height. So again, bi means two, like binomial variables, or bivariate analysis. Univariate analysis is just the analysis of one data point, or one variable type, I should say. Here's a box and whisker plot. A lot of people ask about these, and so I'm going to briefly talk about them. If we measure something over, several different people within a sample, we might end up looking at a bell curve like this. If we divide that bell curve into quarters, or quartiles, they're called, we'd find that 25% of the data would fall from the tail in this bell curve on the right hand or the left hand side to the Q1. About 25% would fall between Q1 and Q2, so in this area. 25% would fall between Q2 and Q3 here. And then the fourth quarter, or the fourth 25%, would fall between Q3 and the far right tail. And so we divide up this bell curve into quartiles, and then we can represent that data a little bit differently with the box instead of the bell curve, which that's the box, and here's the whiskers that go out to the end ranges. If we put the box and whisker on its side, looks like this, and so this is from the end of the first quartile to the start of the third. End of the first to the start of the third. This is 50% of the data fall in here, with the maximum and minimum on either ends of the whiskers. Here's a scatter plot. With a scatter plot or a correlation plot, we're looking at two different variables that are continuous, like height and weight. For every subject, we put one dot, and so you can see that there's a lot of dots all overlapping one another. This data then can be analyzed, and we can look at what is the correlation between height and weight. If the correlation coefficient equals 1, that demonstrates that there's a perfect positive agreement between the two variables. So as height goes up, weight goes up, and there's a perfect correlation between the two. If a correlation coefficient is 0, that means there's no agreement between the variables. So for instance, we might have dots just kind of scattered all over with there really being no rhyme or reason. If we have a -1, that means there's a perfect negative agreement. So for instance, if we had as weight went up, height went down, or as height goes up, weight goes down. That's not what happens with height and weight. It's usually more of a positive agreement. But there are times when one variable goes up and another goes down, and that can go up and down with perfect correlation, and that would be a correlation coefficient of -1. There's a lot of different ways that data can be presented, and there's a lot of different variable types within research statistics. So please let me know if you have any questions. Thank you.